So let's get down to the business of actually trying to read a packet that is represented in hexadecimal notation. And that's what we have on the screen here. So we have a packet in hexadecimal, and on the left, you'll see we have line numbers there. So that's just a way to organize the lines, as several different packet analysis applications will. But for the most part, we're going to be focused on the content here in the middle. And you'll see we have a lot of different hex bytes here. And I even have one highlighted, and we'll talk about that here in just a moment. Now, to reiterate a couple of points I've already mentioned, first of all, a single hexadecimal character is a nibble, and 2 hexadecimal characters represents a byte. So in this case, I have the byte highlighted here, 06. That's 1 byte, with 6 being the lower order nibble and 0 being the higher order nibble of that byte. Now, I want to talk quickly about how to reference bytes in a packet stream like this. So, for instance, you see this is a byte. It's several bytes into what we're seeing here. So, how would we reference this specific byte? I couldn't just say byte 06 or byte 06 because there could be multiple of those within the packet stream. So, how would I reference this byte relative to the other bytes in the packet stream? Well, the first thing to consider is that bytes are counted starting from 0. And I highlight this in red because this is really important, because as humans, we tend to want to start counting at 1. But in computer science, most of the time, we're going to count with 0. So we can count here, and we start with the first byte, which is 45. The second byte is 00. We would actually count those from 0. So the 0 byte is 45. The first byte is 00. So let's count those all the way to the byte we have highlighted. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The 06 byte that's highlighted is the 9th byte offset from 0 here. And I use the term offset, and that's an important term when we're looking at packets in hex, because we're going to refer to everything in terms of offsets, because we're talking about offsets related to the 0 location or the beginning of the packet header that we're currently looking at here. So when we reference the 06 that's highlighted, we're saying that this is the 9th byte offset from 0 in the IP header, or we can denote that by using the 0x9 as listed here on the bottom of the screen. And that's just saying 9th byte offset from 0. And this happens to be the protocol field of the IP header, which is a very important field because it tells us what protocol to expect next after we've already parsed the IP header. And we'll talk about why that's important here in a minute. But the real thing that's important for you here is to understand the concepts associated with referencing bytes. Because as I reference bytes throughout the rest of this course, we're going to reference them using this type of system. So we're going to reference them using offset notation, counting from 0. So if the highlighted byte 06 is the 9th byte offset from 0, then the byte before it, 80, is the 8th byte offset from 0. And again, the most important part here is that you're counting from 0. And that's going to be a little non-intuitive at first, and you're going to make a lot of mistakes and accidentally start counting from 1. I've done it, and quite honestly, I still do it quite a bit. And really, counting from 0 is so non-intuitive that I see a lot of people want to count it out on their fingers. So 0, 1, 2, 3, 4, 5, 6. There's nothing wrong with that, right? I don't want you to feel ashamed that you're having to do that. In any class I've ever taught where I'm teaching people how to count bytes in hex, everyone's using their fingers. They're counting from 0 to 9, and it's perfectly fine. I still do it myself. No shame in it if it gets you to the result you're wanting to do. But either way, if you do feel a little embarrassed by it, I guess it's a good thing this is an online course and nobody can see you do it, right? So again, we're counting bytes starting from 0, and then we're referencing those things, the position of a byte, in offset notation. So the 8th byte offset from 0, or the 9th byte offset from 0, written down as OX8 or OX9. That's how we're referencing those. And we'll continue to do that a lot, and we'll provide a lot of examples that you can work through where you're referencing these things yourself as well. Let's reinforce this with a few more examples. And this is the same packet you're just looking at. I just cleared away this screen, and we're going to go through a couple different examples of referencing packets within the within the hex stream we see here. So the first question is, what is the second byte in this packet stream? And I'll pause for a second and let you think about that one. So the second byte. Now, you might be tempted to say that the second byte is 00, and that's correct, but which 00 is it? So if you look at the beginning, the first first couple bytes of the packet are 45000034, Now you might be tempted to say it's the first occurrence of 0, 0, so that 4, 5 is the first byte and 0, 0 is the second byte, but that would of course be incorrect because remember, we're counting starting from 0. So 4, 5 is byte 0, 0, 0 is byte 1, and the other 0, 0 is byte 2. So the 0, 0 occurring right before 3, 4 is the second byte in this occurrence. Let's try another one. What is the 0 byte? Okay, so this one trips some people up because you're not used to identifying something with a value of 0. But in this case, as we're counting starting at 0, the 0 byte is actually 4, 5. It is technically, I guess, the first byte, so to speak, if you want to think about it in the traditional sense. But for our purposes of starting counting from 0, it is the 0 byte. Let's try another one. What is the 15th byte? I'll pause for a second and let you count that one out. Okay, if you got 80, then you're correct. So what you would do here is start counting from 0, and for every 2 characters, that constitutes 1 byte. So you would start at 4, 5, 0, 0, 0, 0, 3, 4, all the way until you reach the very end of this line. And byte OX15, the 15th byte offset from 0 in this case, is 80, 80. Let's try another one. How would you reference the byte with the value 3, 4? You can find this byte on the first line. You should see it's pretty early on in the packet. And in this case, how would you reference that? Well, you would count starting at 0. Byte 4, 5 is 0, 0, 0 is 1, 0, 0 is 2, 3, 4 is 3. So this is the third byte offset from 0, or OX3, in this packet stream. Let's try one more. How would you reference the byte with the value of AC? AC is found on the first line towards the end. So find that and count out the value there. If you count it out, you should come to OX12. So AC is the 12th byte offset from 0 in this packet stream. So hopefully this gives you a couple practical working examples that you can go through to kind of understand what we're talking about when we talk about counting out bytes. This is an incredibly important thing, and we'll also provide several examples that you can work through independently to try this out on your own as well. So we've talked about how to understand hexadecimal representations of data and how that compares to binary and decimal data. And moving towards our goal of being able to manually navigate packets, the last piece of the puzzle is the map that we're going to use to do that navigation. Obviously, if you're going to get from A to B, you have to have a map that tells you how to get there. So packet maps are really our way to do that. And I have a couple of them on the screen here, and you can see it's really just a graphical representation of packet fields based upon protocol headers. And of course, we discussed protocol headers in the last lecture and how protocols were rules governing the communication between systems. Those protocols, their specifications contain certain data structures and fields that are required in the communication to make that happen. Now, we can take those protocol specs and extract them into maps just like what we have here. And so we have 2 of those. We have one for Ethernet and one for IPv4. Those are the different headers, and these are the different fields in them. So these are the maps that we're going to use to navigate packets, and these will become your best friend as you go through some of these exercises. So you'll notice in the materials with the course, I provided PDFs of several of these, really all the ones you'll need for this course. And you want to download those, keep them handy. Honestly, what I recommend doing is printing them out, maybe even laminating them or putting them in some sort of notebook that you can keep handy. I actually have mine laminated that I keep in my backpack, and I actually have a smaller set I keep digitalized or in digital form on my phone and on my iPad for quick reference. You want to keep these handy because you never know when you might need them, and certainly I don't expect you to memorize all these different protocol headers. Now, the packet map, I've broken them down. They're actually created in Excel here because they show you the different the layouts of the packet header based upon the byte offsets. So if you look at the IP header here on the right, you see that we have byte offset 0, byte offset 1, byte offset 2, and so on. So we're breaking this down by byte, and you'll notice that different fields have different lengths. So in byte offset 0, we actually have 2 fields represented. The version field in the higher order nibble of byte 0, and the IP header length field in the lower order nibble of that same byte. That's different than byte offset 1, which is a single byte used for an entire field, in this case the type of service field. And then you'll see even in byte offsets 2 and 3, we have a single value spanning multiple fields. So these fields can be variable size, and that's why our knowledge of how to convert from hex to decimal and understand the binary representations of data, that's why it's so important, so we can parse these things appropriately. And we're going to go through a couple really great examples breaking down packets using this data. But the packet map, hopefully it's somewhat based upon what we talked about thus far, self-explanatory. It's just the layout of different fields and where they occur in the layout of the overall header and the overall byte structure of the data we're looking at here. So again, this will make a lot more sense as we go through some examples. I do definitely recommend maybe even pausing the video right now, going and actually grabbing those packet maps I provided you, printing those out, getting those somewhere maybe on a second screen if you have a second monitor, or maybe on an iPad or something, so you can look at those alongside the exercise we're about to do here. So let's use our packet map to navigate this packet. So we're going to take this individual packet and break it apart into the different protocol headers by examining specific fields based upon what we know about them from our protocol maps. Now, the packet maps don't tell you what each field does. That's an exercise left to some degree to the reader, although we'll get to that and talk more about that in much more depth when we go through individual protocols later in the course. But for now, you'll have to kind of, if you don't already know what some of those fields do, you'll have to do a little bit of looking them up. But I'll try to explain some of them as I go, at least for a couple of these examples. And for the more important ones we're going to look at now, detailing the length of certain protocol headers and the expected next header. So we're going to start with this, and the first protocol we're going to look at is the Ethernet protocol, because if you remember from our discussion on encapsulation and decapsulation, we're building this packet, adding different protocol layers until we get to the bottom of the OSI model, that data link layer, and then it's handed over to the physical layer for actual transmission, and then the packet is decapsulated in reverse order. So on the receiving system, the first bit of data that the receiving system is going to see is that data link layer protocol, which in this case is going to be Ethernet, and for the most part is going to be Ethernet for a lot of the network communication that you see. So since we know Ethernet is what we're going to be expecting here, we're going to start by looking at the Ethernet packet map. Now, you can pull this up independently yourself, and I certainly recommend doing that for these exercises and keeping that side by side, because I won't have this on the screen at all times. But we can learn a couple things about the Ethernet header here already. The most important for our purposes is the length of the Ethernet header, which is fairly static. If you look, we start at byte offset 0 and go to byte offset 13. So starting, if we're counting from 0, that means we're talking about 14 bytes right here. So we're talking about a 14 byte Ethernet header, and then we have this variable length data section. And that data section is actually all the remaining packet data. So everything after the type field is all other packet data, so other packet headers. So we're talking about an Ethernet header that is only 14 bytes long. And fortunately for us, we know how to count off 14 bytes. We know how to do that and count that out and identify that. So we can very easily identify the Ethernet header, so the data link layer header in this packet, just by counting off 14 bytes. So let's do that. So here we've highlighted and underlined in green the Ethernet header, and this is 14 bytes, starting with 00 all the way to starting with 0005 all the way to 0800. These 14 bytes represent the Ethernet header. Now, this brings up a couple good questions. We know the Ethernet header is here, but how do we know what's next? How do we know what to look for next? Fortunately, that information is also provided in the Ethernet header. We can actually look to that to see what protocol is expected next. So let's go back to our Ethernet packet map and look to see if there's any information here that can help us determine what the next expected protocol header is. And we're in luck. That actually exists in the Ethernet header, and it actually exists in the type field that begins in byte offset 12 and spans over to byte offset 13. So it's a 2-byte field, and this type field, which is also known as the ether type field, its exact purpose is to tell us what header is expected next. So when a computer receives a packet and it reviews the Ethernet header, before it gets to the end of it, actually right at the end of it, it's going to tell it what to look for next. So that way it knows how to process that information and what part of the operating system to hand that data off to be processed. So we have this type field. Now, if we look back again at our Ethernet header, we see that the last 2 bytes of that header are 0800. Now, you can go out and look up all the different Ethernet type fields and what they mean and what they signify should be the next protocol. In this case, 0800 corresponds to IP, and specifically IP version 4. So it's telling us, and it's telling the receiving system that's taking in this packet, that the next bit of data immediately after this should be the beginning of an IP header. So we know what we can look for next, and we can take our IP packet map and use that to start processing the next set of information we see. Here's the IPv4 packet map, and it's quite a bit more involved than the Ethernet packet map we just looked at. There's a lot going on here. There's several fields spanning multiple bytes. There's some that span individual nibbles and some that span individual bits. And we also have this whole concept of a variable length header. So whereas the Ethernet header is going to be fairly static and always be the same length, the IP header is going to be variable based upon a number of options that may be used with the IP protocol from the transmitting system. So that changes things for us a little bit, but nonetheless, there's a lot of information here that we can use to kind of map out where this header begins and ends. We can't just count out 14 bytes like we did with the Ethernet header. We actually have to see what the length of this header is. And you can probably look at this and immediately see how we're going to do that. In byte offset 0 in the lower order nibble, there's a field called IP header length, which is a 4-bit field, and we can use that to determine how long this header is. And that's exactly what we want to do, is we want to determine what the length of this field is so we can count off that number of bytes and mark that off as our IPv4 header. So let's do that. Looking at the packet and looking at a couple of these initial fields, starting at byte offset 0, so the first byte, we see that there are two fields here. The higher order nibble is the IP version field, and it tells us what version of IP we're dealing with. In this case, it's 4, which is also decimal 4, and that means we're dealing with IP version 4. So that's expected. And then in the lower order nibble, we have the value of 5. Now this is a calculated field, so when I look at 5, it doesn't mean that the header is only 5 bytes long. That wouldn't be enough. It's a calculated field, and you take the value of this field and multiply it by 4. So in this case, the value is 5. We multiply that by 4, we get 20, and that tells us that the IP header in this packet is 20 bytes. So knowing that, we know where the IP header begins and ends, and we can successfully mark that off as I've done here. Again, 20 bytes starting at 4.5, ending at 6.8, and the area underlined and highlighted in orange is our IP header. Now that we know how long the IP header is, we're left with a similar question as we faced earlier with the Ethernet header, and that is knowing what protocol header to expect next. Now, if you're familiar with normal transport layer protocols, again, we're moving from the network layer to the transport layer now, you know that it's probably TCP or UDP, but you don't know that for sure, and you certainly don't know which one it's going to be quite yet. So what we need to do is look at the IP header and see if there are any fields that will tell us or give us any clues as to what the next expected header is. Sure enough, there is such a field, and it's the protocol field found at byte offset 9. You should see there that that's a 1-byte field, and the purpose of the protocol field is to tell us what the next expected protocol is after the information is processed from the IP header. So what that protocol is that we're going to be looking for and expecting next, so we know how to parse that appropriately. And that's in byte offset 9. So we can identify byte offset 9 here, and I've highlighted it here in red, and it has the value 06. Now, once again, there's a chart you can look up to see what the expected values are here and what each one maps to, and there are certainly a lot of options. In this case, we see 06, which maps to TCP. So this tells us that immediately following the IP header, we're going to encounter TCP data or a TCP header right here, and we need to parse that using a TCP packet map. So you should see kind of the theme we're building upon here. To dissect these packets into their different headers, we really generally need to answer just a couple of questions. Every time we encounter a specific protocol header, we need to identify how long it is and then what happens next, so what the next protocol is. We did that with Ethernet, and we did that in a very similar way with IP, and next we have TCP, which we can process accordingly, and if there's another protocol there, we could look at it. But first, let's see what we have with the TCP header that is coming up next. So here we have a TCP packet map. Once again, this one is maybe even a little bit more complex than the IP header we looked at before. And it also has this concept of TCP options, meaning there's a variable portion of the packet. You can see that at the bottom of the screen here. We have that variable portion. So a TCP header can be a variable size. So we have this lingering question of, we know the TCP header is what we're expecting next, but how long is it? How much of the remaining packet data does it take up? And is there anything remaining other than the TCP header? Now, in this case, we have another field that will help us here, and you can see that pretty immediately in byte offset 12. The higher order nibble here is the header length field. And that header length field is going to tell us the exact answer as to how long the TCP header is, so we can map out the next portion of this packet. In this case, we can count that off here, and we see that in that byte, the 12th byte offset from the beginning of the TCP header is 8. The higher order nibble is 8. Once again, this is a calculated field, so the value is not simply 8 bytes. It's a field we multiply by 4, and that gives us a total of 32 bytes. And that's telling us that the TCP header, in this case, is 32 bytes long from the beginning of the start of that header. So starting at 06, we count off 32 bytes, and that actually takes us to the end of this packet, and that maps out the whole thing. So in this case, there's no additional data, no application layer protocol. So this is just a TCP packet, likely a TCP control packet, some type of flow or sequence control, since it has no data with it, like a SYN packet or a SYNAC packet or something like that. We could go in and break that down a little further, but we're going to leave that to a later exercise. But nonetheless, that tells us exactly where the transport header is, and that ultimately gives us the completed mapped packet. So we see here in green, we have the Ethernet header, which is 14 bytes. We have an IP header, which is 20 bytes, and we have a TCP header, which is 32 bytes, making in total a 66 byte complete packet. Now, to reiterate, really the questions we answered in almost every step along the way here are, given the knowledge of the current packet header we know about, how long is that header, and then what packet protocol, what header comes next, right? Those are the questions we did every step along the way for Ethernet, for IP, and for TCP. Ethernet was a static header size, so that was pretty easy. For IP, we had to look within the header itself to determine the length of the data in this case, and the same for the TCP header. We had to find that within the packet. So again, this is done very systematically, and it's done so that systems, when they decapsulate this data and review it, they can navigate this pretty seamlessly, right? You can see how a machine could be able to navigate this pretty easily, and that's exactly what we're doing. We're just doing this as a human-centric process here, and that's how we get to this this beautifully mapped packet with this nice rainbow of colors. Let's go through one more example of navigating a packet using packet maps. This packet's on the screen here, and we're going to go through a similar process, but I'm going to go a bit faster, and I'm not going to stop and show you the packet maps that I've already gone through. If you want to get that ready, definitely get that and have it beside you and take a look at it as we go through. And you may have to pause and go through a couple times if you want to work through this on your own, but I'm going to go through it fairly quickly here. So we have our packet, and again, we're going to assume that it's starting with an Ethernet data link header here, because all the examples we're going to look at are going to do that. Now we know the Ethernet header is 14 bytes in length, so we can start by very easily just mapping out that first 14 bytes as I've done here. They're highlighted in green, and this first 14 bytes constitutes the Ethernet header. So we know the network layer protocol is next, and to find that, we have to examine the header info field in the Ethernet header, and that's located at bytes 12 and 13 offset from 0 in this header, which is the last 2 bytes in the Ethernet header. So let's look at those and map those out. In this case, that byte, those bytes are 0800. The same as the last example, this ether type indicates that the following network layer header is the IP header, IPv4, so that we know that that's what we need to look for next, and that's what the packet map we need to use to parse the data that follows the Ethernet header. Digging into this data and looking at our IP header information, we see that, of course, this is IP version 4 by looking at the higher order nibble of byte 0, and we can find the length of this packet header by looking at the lower order nibble of byte 0. In this case, that value is 5, and this is a calculated field. So we multiply 5 times 4 to come up with 20 bytes. And that tells us that the IP header, in this case, is 20 bytes long. Knowing now that the IP header is 20 bytes, just like our previous example, we can simply count out those 20 bytes, starting at byte 0, which is identified by the value 45, starting there and just counting out those 20 bytes to identify the IP header, which is marked here with orange and clearly identified. Now, that gives us the Ethernet header and the IP header. The next question we have to answer is what comes next. So following the IP header data, what additional header information can we expect next in this packet? And to find that answer, we're going to look within the IPv4 header at the protocol field in the 9th byte offset from 0. That's going to be the field that tells us what protocol to expect next as we are going through this decapsulation process. In this case, that field has a value of 01. Now this is different from our last example where we had a value of 06, which indicated TCP traffic. Was TCP header is what we could find next. In this case, we have 01, which indicates that an ICMP header or Internet Control Message Protocol header is next. Again, you want to have the ability to be able to look up these field values, so definitely take a look and see if you can find a list of those now and understand how to perform that process, because certainly over time you'll encounter new protocol field values that you've not encountered before, and you want to have the ability to see what those values mean. Again, half the battle here is the ability to identify interesting protocol fields and look up the possible values and understand what could go there and what it means to your investigation. Now, in this case, we know ICMP is next, and I said I wouldn't show any more protocol maps in this section, but since we haven't talked about ICMP, I'll show it up here briefly so we can talk about it. Now, don't worry about understanding ICMP in depth. We have a section later in the course where we're going to go much more in depth with ICMP and the specifics. But for now, just know that generally it's a pretty simple protocol in which there's a standard 4-byte header, and based upon the contents of that header, that determines the remaining content of the ICMP data section. So in this case, we have the message type field, the message code field, and the checksum field. And then we have this variable data section. The variable data section is dependent entirely upon the message type and message code fields, and we can have a lot of different variations of ICMP packets based upon this. That's why we only identify the static content of the 4-byte header. So since we know it's 4 bytes, we can definitely map that off pretty easily. And that's what I've done here. In this case, in blue, I've marked off the ICMP header, which are these 4 bytes. Now in this case, the type and code fields are the first 2 bytes, and we can go ahead and identify those as well. In this case, the first byte, 08, means type 8, and 00 means code 0. So this is a type 8 code 0 ICMP packet. And if you actually go look that up, you can find a list of all the different types and codes, and we provided that in the materials with the course as well. You'll see that this is an echo request, which is essentially a ping, if you're familiar with the ping command and pinging a workstation or pinging a system from another system. This is exactly what this is an echo request. So in this case, we know that these 4 bytes represent the ICMP header, and based upon that, we know that all the remaining data is ICMP data related to that ICMP header. There's no additional embedded protocols that are going to be going on here, at least with this packet. There are certainly things that can happen with ICMP double-headed packets where you have an ICMP packet inside of another one. That's a little beyond our scope here. We'll talk about that later. But for the most part, what you need to know here is that we have the 4-byte ICMP header, and the rest of this is ICMP data that is based upon that header information. And we could just mark this all as ICMP data and leave it at that. I've gone a step further and actually separated the ICMP header from the ICMP data in this course, just for illustrating the difference here. But overall, we have our mapped packet now. We have an Ethernet header that's 14 bytes, an IP header that's 20 bytes, an ICMP header that's 4 bytes, and remaining ICMP data that is 36 bytes, making a total sized packet of 74 bytes. And thus, we've mapped out this entire packet. Once again, remember, The process here, we're thinking kind of like a machine, and that we start at the beginning, and knowing the first protocol, we can use the information within that protocol to see what the next protocol is. And from there on, we can use information within the protocol we're currently examining to see the length of the existing protocol header and what comes next. Again, those are the two questions you always need to answer. What is the length of the header I'm currently looking at, and what is next? What packet map can I use to explain what I see next? If you can do those two things, you're not really going to encounter too many protocols or too many packets in hexadecimal format that you can't dissect. So again, we want you to continue to practice this, but again, remember those two questions and how to find answers to them, and you'll be fine. This one was kind of a doozy, but that's going to bring us to the end of this lesson. Now, the things we learned here were that packets are often viewed in hexadecimal for concise, easier reading. It's a lot easier to read a packet in hex than it is in binary and even in decimal. So hexadecimal is really the choice for manually dissecting raw packet data that's not abstracted to some other type of representation by a packet sniffer or packet analyzer tool. To analyze packets in hex, we use packet maps, which can be used to visually parse them and kind of guide us along to understand what fields exist and what we're looking for. Packet maps are really the key to visually dissecting packets, like we just did in several examples. Now, when doing this, protocol headers, when we're looking at a specific header, is going to provide us generally all the information we need to determine where that header ends and what's next. That's really the key to dissecting packets as you go through this type of analysis. And finally, the ability to read packets is important, really in many disciplines, and we kind of hit on this in a couple places. But eventually you're going to encounter packets that are maybe malformed and not parsed correctly, or maybe there's something you don't have a specific parser for, or maybe it's a custom protocol, maybe it's part of malware communication or some type of attack or something of that nature, where you need to be able to understand what's going on in the packet and parse it out into individual values, independent of something that a tool like Wireshark might do for you. Now, some people in their profession may not actually run into this stuff, but I think to some degree, if you do this long enough, you eventually will. And nonetheless, it's very important to have this kind of fundamental understanding of how the packet analyzer you're using works to process packets. Ultimately, the general philosophy with any type of analysis is the further abstracted from the data you are, the more opportunity there is for biases to enter in your judgment and for mistakes to be made. Understanding the things in this lesson in particular are going to help you be less abstracted from your data and more understanding of what's occurring at the source, and make you ultimately a better packet analyst. Now, again, I recognize some of the material in this lesson in particular is a little bit intense, especially if you've never done anything like this before. My strong recommendation is to go through some of the exercises I provided here and actually practice this. It's one thing for me to go through examples and show you, but until you practice it yourself and kind of enter some of that mental strife of not being able to figure it out and working through it and finally getting to an answer, that's really going to be your best way to learn. So definitely go through those exercises, go through that and practice the process of identifying specific bytes, moving through packet headers to map a packet, and so on. That's going to be very critical to understand what's going on in this lesson.